Good morning. So, in the last class, we concluded our discussion on de Broglie waves, the so called matter waves, and we pointed out that in spite of the experimental evidence, there are a few loose ends which we have to settle. It is not that they have been settled, but I encourage you to think about the fact that if you apply the usual formula that velocity is the product of frequency and wavelength, then you get contradiction between the particle velocity and the wave velocity. We then went on to introduce the topic of the so called fundamental constituents of matter, which were called atoms in the ancient days. In our country they were called anus, and I gave a sort of brief historical introduction as to how different civilizations and different scientists conceived of atoms. So, as I told you, the major fillip came actually from chemistry and thermodynamics. So, we said that periodic table had a very great importance in actually solidifying the concept of an atom, because it introduced the important concept of an element. What I then started to discuss was the famous experiment conducted by Rutherford. So, I believe that I stopped at that particular point. I showed you the apparatus, which I will show you again today. I will describe what the apparatus is for the sake of continuity, and then we will see what the results are. So, these were the things that we discussed, and this is the apparatus. So, this illustration, this is of course not a photograph of the apparatus or a drawing. So, you have this lead shield which contains the radioactive source bismuth 83, that is, it has 83 protons the way we understand today, and it emits alpha particles. Alpha particles carry an energy of 5.5 million electron volt, so they are highly energetic. Then there is another lead shield here, some kind of a plate which has a thin hole, and therefore it acts as a collimator. Lead is a very good absorber otherwise, and then this golden looking plate is the foil, very thin foil on which the alpha particles impinge, that is what we have, and then they get scattered all around, and it is schematically shown through these scintillation plates which are made of zinc sulfide, which were actually moved around. It is known that the gold foil carries a whole lot of charge, close to 100 let us say, and my alpha particle itself carries 4 units of charge, 2 units of charge, and that is something that we have to remember in the analysis. So, this experiment was a crucial experiment to decide whether the Thomson model of the atom was correct or not, and the Thomson model itself was illustrated in this figure. The second sphere that you see here, that is what you have. So, you have a kind of semi-solid sphere, let us say, which is in which the positive charge is continuously distributed, and these yellow dots actually show us that electrons are probably spread around in this solid charge. In other words, we are assuming that the positive charge is not a particle in that sense, it is an extended object. We only want to assume that electrons are really much smaller than the positive charge, and we know today that it is not completely correct. Okay. So, this is the experimental apparatus, and these are the details. As I told you, source was bismuth, energy was 5.5 MeV, and the target was really very thin. So, we have to remember that it is so thin that it has only a few layers of the atomic charge, atomic distribution. That means there was also an assumption or an understanding that the atomic size is of the order of, let us say, 10 to the power of 8 meters, or maybe 10 to the power of 9 or 10 to the power of minus 8 meters. Therefore, the crucial question to be settled by the experiment is whether the positive charge is distributed over a region of something like 10 to the power of minus 9 to 10 to the power of minus 8 meters. That is a very important thing. If you do not remember this, then the result cannot be easily appreciated. So, this is where we had stopped, and we will now continue to look at what we are going to get. I do not have a curve for Rutherford's experimental result itself, but here are some curves for scattering of proton on gold, proton on platinum and proton on boron, and you see that they all show a universal feature. So we don't have gold is common to both of them. So if you look at the green line there, if you look at the green line here, what we find is that we have simply replaced the alpha particle by the proton, and the energy is a little bit smaller, about 2 MeV instead of being a 5.5 MeV alpha particle. It does not matter, but you see that all these scattering cross sections have a universal feature, namely they are quite large in the forward scattering. So this is the recoil angle. So theta equal to 0 is like forward scattering. The particle simply goes unscattered, let us say, and as you keep on increasing the value of theta, then it starts getting scattered more and more. I will illustrate that in a minute. But the most important thing is that even when you come to very, very large angles, so we are speaking of something like 180 degrees, even when you look at the back scattering, 180 is what? The particle goes and then turns back. Even when you do that, what you find is that the scattering cross section is not equal to 0. So what is the picture that we have, and let us show that. So the main understanding here is that all the scattering is taking place because of the positive charge and not because of the negative charge. There is a good reason to make this assumption. That is something that we have to know. The thing is that the atom is very, very heavy compared to an electron. Remember, an electron has a mass of about 0.5 MeV by c squared, whereas an atom is 2000 times heavier than that. And our alpha particle is coming with an energy of 5.5 MeV. So if a projectile which is 10,000 times heavier than the target were to hit the target would be ripped off. Mean the electrons would all be flying all over the place. That is not what is happening in the Rutherford cross section. The projectile, the 5 MeV alpha particle is getting scattered and we don't see too many electrons. In fact, we don't see any electron. Therefore, it is to be assumed that the projectile is hitting a target which is of comparable mass. In fact, it is of larger mass, because as we saw, if you assume gold has, let us say, about atomic mass of about 150, I don't know what the mass is, it is certainly about 50, 60 times larger than, at least 40 times larger than the alpha particle. So if you look at it from that particular viewpoint, what we find is that the scattering is essentially against a stationary target and a very heavy target. So we are interested in the scattering of what? A relatively light particle by a relatively heavy particle. We have to remember that. Now if I come back to this particular figure, so this is my positive charge distribution. So maybe I will use another sheet to illustrate that. So I have my positive charge distribution sitting here. I am not assuming that there are so many plus particles. It simply says that this region is filled with a positive charge. Now, even if you do not know how to solve the problem, a good question that we can ask is, what is it that we expect of the scattering? That is something that we can ask. Now, imagine the projectiles are coming like this. The area over which the beam is spread is much, much larger than that of a single atom, obviously. Now, the field produced by this, let us take it to be a spherically charged distribution, is 1 over r squared outside the sphere. One over r side outside the sphere, that means it drops off very, very rapidly. So if my beam is very far away, it virtually passes unscattered. That is the statement that we are making. All of them have the same energy. So essentially, scattering is characterized by the impact parameter. The strength of scattering is characterized by the impact parameter. And remember, impact parameter is the approach of the shortest distance. Now if I look at a look at an alpha particle, a projectile particle which is relatively close, this of course will be repelled by this charge distribution. So what will happen? It will come here, and because of the repulsion it will go in this direction, and now from this center we can calculate what the impact parameter is. This is a completely symmetric situation. The particle here will be repelled by this, and the particle far away here will go straight away, and that is what we are saying. Since the field is rapidly falling away, most of the particles are not scattered, and you see that in that particular, in this slide, where you have a very large number of alpha particles which are coming in the forward direction close to theta equal to 0. So the scattering angle is obviously with respect to the incoming angle, and this is the theta that we have in mind, how far it goes. An exceptional situation or an important situation is when the particle is coming head on. So this is the center of my charge distribution and my particle is coming. Now depending on the energy of the particle, if the energy is not very large enough, at some point the potential energy matches exactly the kinetic energy. It is very easy to work out. Half mv squared is equal to q1 q2 over 4 pi epsilon naught d, where d is the distance of the shortest approach. Q1 and Q2 are the charges that are carried. At this point the particle comes to rest and it recoils. That is what is going to happen. Now when it recoils, that is the cross section corresponding to 180 degrees. But then if the energy is large enough to penetrate this charge distribution, and that is very easy to work out. So if the radius of this charge distribution is r, what we are going to do is to replace d by r. So if my kinetic energy is larger than this threshold energy, then what happens? The charge particle, alpha particle, would penetrate this charge distribution. Now once you penetrate this charge distribution, things change, because here the electric field will actually start decreasing as you approach the center. That is what is going to happen. So here the electric field was increasing, here the electric field will start decreasing as we approach the center, because you have the great figure which depicts how the electric field behaves inside a sphere. Please take this to be a sphere. So inside it is linearly rising, because it is like a harmonic oscillator potential, and outside it falls off like 1 over r squared. So this is 1 over r squared and it is linearly rising. So as it enters, the electric field actually decreases, the repulsive force decreases. At the origin, exactly at the origin, there is no electric force at all. It comes here and it moves, and we should be able to see that. In other words, the whole question of the so-called backscattering, whether the particle comes and gets rebounded here or the particle continues to move here, depends on two aspects. One is whether the energy is enough to penetrate this charge distribution, and that is tied with what this r is, what the radius is. So if I draw another line, what the radius is. If the radius becomes smaller and smaller, the energy required to penetrate it becomes larger and larger, and in fact if r goes to 0, if all the charge is concentrated at one particular point, then there is no way that my alpha particle will be able to pass by the point charge, because there is always an r for which, what are we saying, half mv squared is equal to q1 q2 over 4 pi epsilon naught d. If I write, there is always a d which will satisfy this, because d can be made sufficiently small, therefore this quantity can be made sufficiently large. Therefore whether the Plum pudding model is correct or not depends on what the energies are, depends on what the charge distribution radius is, and what kind of scattering we are looking at. This is the way we should understand Rutherford experiment. Now there is an although I have given this kind of an analysis, you can do a very simple calculation. So let us say z is of the order of 100 without any loss of generality. Gold probably has a much lesser number of charges. Your energy is something like, projectile is 5.5 MeV. So if you did that, you can ask what is the shortest distance my gold particle my alpha particle can approach the gold foil. That is a question that we can ask. If you work it out, you will find it, please take it as an exercise, it will be a tiny fraction of an angstrom. It will be the tiny fraction of an angstrom. So if your analysis were based on just the recoil, then we are not going to really get much information about the distribution of charge inside an atom. Is that okay? Except that it tells you that if the charge distribution is there, it is occupying a much smaller space in the atom. So this problem is not difficult to work out. So what we are saying is that my atom has a size of something like 1 angstrom, and we are saying that if you work out this problem, my charge distribution is actually of the size of what? Probably a fraction of an angstrom. That is what we are saying. That means there is no uniform charge distribution throughout the atom. But it does not tell you exactly what the size of the charge distribution is, because suppose you got something like a 0.1 angstroms or some such thing, which is 5 times smaller than the size of the hydrogen atom. For the case, in the case of gold, it is a little bit more complicated, but if you got a number like this, it is not going to tell me much about the size of the nucleus, but in spite of that, you should perform this calculation. It is not a difficult calculation to perform, so please ask, given the Z of the gold, how close these backscattered alpha particles could have approached. That puts some kind of an upper limit on the size of the charge distribution. But the real input or the real answer comes not simply from the backscattering, but from something different. And this is a very important result. So we should not only look at the number of electrons or the alpha particles that are scattered backwards, we should actually look at the complete angular distribution. Normally your books tell you that Rutherford found that most of the electrons were not scattered and a significant number of them were actually coming back. Of the scattered electrons, a significant number of them were coming back because of the 100% recoil. That is what we showed at 180 degrees. That is not enough for us to draw a quantitative conclusion. We should actually look at the complete angular distribution, and Rutherford indeed did that experiment. In this figure, for example, we showed that the detector was moving all around the circle and it was collecting the scattered alpha particles. That is something that we have to remember. Okay. I cannot work out the theory for the scattering of an electron or of an alpha particle in the field of a nucleus, but one thing all of us know is that Coulomb interaction is uncannily close to gravitational interaction. So let me write that here. So my gravitation is G mm by r squared. My Coulomb is Q1 Q2 1 over 4 pi epsilon naught by r squared. Both of them are inverse square laws. So purely numerically, if I were to make a mapping, Q1 Q2s are like the two masses, 1 over 4 pi epsilon naught is like your G in some units, the SI units, and you have an r squared. And we know when Newton propounded his gravitational law, he solved the problem of not only the bound planets but also comets which may never return. What is it that we learnt? What Newton taught us was that in general, this is very important for us. So in an inverse square field, what do I mean by that? Force goes like 1 over r squared most general trajectory, the path is either one ellipse. In special cases, this ellipse can become a sphere at one end and a straight line in the other end. That is what you have. And secondly, the second is a hyperbola. So essentially conic sections which can actually become a parabola. This is what we find, if it is attractive. If it is repulsive, there is no question of being an ellipse, because we are looking at a repulsive scattering. So, all trajectories are hyperbolas. That is what we have. So, if I were to write the scattering again, so this is the scattering center, my positive charge is coming, this is also positive q1, this is some small q, then when it goes and gets scattered like this is actually a section of a hyperbola. This is a section of a hyperbola. So, that is what we have. So, now we are going to ask what is the probability that this particle is going to get scattered at this angle theta. That is the question that we are asking, and Newton actually solved the problem. So, in the case of planetary orbit, of course, you have hyperbolas if the energy is greater than 0, and we know some comets return, that means they are in highly elliptical orbits. Some comets never return and they are in these hyperbolic orbits. Newton had already worked it out. That is a very, very important thing for us. Therefore, we know if we start looking at the scattering cross section, the number of alpha particles that come at different angles. Here is an illustration. This is not exactly Rutherford scattering, but it is some other scattering, but never mind about that. If your charge distribution was over a reasonable volume of the atom, then your cross section should look like this. It comes here, there is a bump, it comes down, there is a bump, it comes down, there is a bump, so on and so forth. So, it is as if there is a continuously falling curve as I keep on increasing my scattering angle, but suddenly there is some kind of a trigonometric function which is superposed over that. For example, if you can imagine, remember your LCR circuit where you have a damping, it oscillates and falls down, oscillates and falls down, that is what is happening. There is something similar to that, and this is a hallmark of a scattering from a extended charge distribution. This is something, and this is an experimental result and is confirmed by theory. Okay. But if you look at this, which I showed for scattering of hydrogen on gold, you do not see any bumps. It is a very, very smoothly falling function, and therefore, from this we can conclude that if at all my positive charge has a certain distribution, it is very, very small compared to the size of the atom. That is a very important result. This is a illustrative result, but actually I have one result coming from Geiger and Marsden. Geiger and Marsden were students of who? Students of Rutherford. They very carefully did a fitting of Rutherford results. So, the circles are experimental points. Okay. This is the scattered number of alpha particles that he is going to look at. Now, the so called Rutherford formula is the theoretical expression assuming that all the charge is concentrated at one point, and you see that the experimental numbers are in complete agreement. You barely see any difference at all. They are in complete agreement with the theoretical curve. That means, if at all my charge is distributed over a certain volume, it should be a tiny, tiny fraction of the atomic size. In fact, if you estimate that, you find that the distance over which my positive charge is distributed is 10,000 times smaller than the size of the atom. This is the most important result of Rutherford experiment. So, what I mean to say is that a careful, detailed, quantitative analysis is a very, very important factor in interpreting these results. We cannot simply go by qualitative reasoning. So, even though at this point you do not know how to derive this formula, you should know that Rutherford and his students, Geiger and Marsden, they did a fairly accurate and a careful analysis before they drew the conclusion that the positive charge is concentrated in a very small region. Okay. What is a natural consequence? The natural consequence is the planetary model. So, let us go back to the atom. We have been looking at the scattering. So, what we are saying is that my atom has a size of, let us say, an angstrom. 1 angstrom is 10 to the power of minus 8 centimeters, which is 10 to the power of minus 10 meters or 0.1 nanometer. That is what I have. it is of the size of an angstrom, that is what I have. And now I am saying this is the size of the atom. Now I am saying all the positive charge is sitting here in a very small region, and this is probably something like 10 to the power of minus 13 centimeters or 1 femtometer. 10 to the power of minus 15 is called a femtometer, that is what it is sitting. And we know that in an atom we have discrete number of charges. The total positive charge is equal to the total negative charge, they are the electrons. The force between the positive charge and the negative charge is of course attractive. So what do? We go back and fall upon the Newtonian result, and what we have is essentially a planetary model. If these orbits are bound, these are probably moving in orbits like this. This picture or this cartoon of course is made in more recent days, when we know that that positive charge distribution itself is consisting of protons and neutrons. Even these discoveries were made by whom? Were made by a student of Rutherford. Chadwick discovered the neutron. Protons were already known in the cathode rays, that is what we have. And we imagine that our electrons, which are denoted by these red crosses, they are all moving in orbits. This is from Encyclopedia Britannica. This of course is very schematic. You should not assume that there are 2 electrons per particular orbit, or you should not assume at this particular point that all orbits are circular, because when we discussed or when you studied Kepler's laws, what did Kepler tell us? Kepler told us that the planetary motion is all elliptic. Sometimes it can become circular. So even here the lesson that we have is that the orbits are elliptical and electrons are distributed over them, and the center of attraction, the center of the force, the positive charge, is in a very, very small region. This picture is of course not to scale. There is the mandatory warning, because this makes it appear that my protons and neutrons are occupying a large region in space. That is not correct. As we told you, it is a very, very small number. Okay. So this was a hallmark, and at this point you see that we have all completely forgotten about photoelectric effect, Planck hypothesis, de Broglie waves, everything. I suddenly started motivating you about what? The ultimate structure of the matter, ultimate fundamental constituents of matter, by looking at electrons and wave-like behavior and so on and so forth. But actually what we are going to do is quite tied up with the idea of a quantum, and that is because although the planetary model, where you imagine that all the electrons are going in circular or elliptical orbits, may be consistent with the results of Rutherford scattering, they are not consistent with other aspects of electromagnetic theory. So what we have to now do is to go back and ask ourselves what we know from Maxwell's equations or electromagnetic theory. So I am going to summarize it very qualitatively. So the first statement is that charge at rest what does it do? It produces electrostatic field. So you can think of a single point charge, so it will produce 1 over r square field. Now if the same charge is moving with a velocity v, not only will it produce an electric field, it will also produce a magnetic field, because a moving charge constitutes a current. That is what we have. So this produces electric and magnetic fields. This produces electric and magnetic fields. That is what it produces. The operative word here is, this is uniform. That means no acceleration. So now the question that we are going to ask is, what happens if I take a charged particle and it starts accelerating? So this acceleration can be linear, or it can be going in a circle, or it can be the charged particle can be otherwise oscillating up and down, so on and so forth. So obviously when the particle is accelerating, except perhaps at one or two instants, it also has a velocity. So it should be producing E and B, electric field and magnetic field, but now there is a difference. It produces a special kind of electric and magnetic field which corresponds to electromagnetic wave. So in your chapter on electricity, magnetism and optics in your class 12 NCERT book, you people studied or learned that what we call as light is nothing but an electromagnetic wave. So what is happening? If a wave is propagating in some direction, then my electric field will be one direction and magnetic field will be in the other direction, and E cross B will be the direction of the propagation. So you have learned quite a lot about polarization, direction of the electric field, linear polarization, so on and so forth. That is what you have learned. So basically what is happening in a physical way is that when you want to accelerate a particle, you start pumping in energy, and when you start pumping in energy, part of it will go to increase the energy of the particle, part of it will get liberated and it will become electromagnetic radiation. So what is happening is that if a particle is accelerating, it also starts emitting radiation. Of course, to accelerate a particle, you don't have to pump in energy. For example, if the moon is going around the earth is going around the sun, nobody is supplying any energy, but then it is accelerating because it is in a circular orbit, and the fact that an accelerating particle emits radiation is valid for all kinds of acceleration. That is the very, very important thing, and it is a uncontested consequence of Maxwell's theory, electromagnetic theory that you have read. And now you see, if you look at this picture, the outer electron is going in one orbit, the inner electrons are going in another orbit, they have all accelerations given by mv squared by r. So what should happen? The outer electron, for example, should gradually lose energy, come into this orbit, this should gradually lose energy, come into this orbit, so on and so forth, and eventually all the electrons should lose their energy until they collapse inside the positive charge distribution, the nucleus. That is what should happen. So in other words, we have a serious problem with the notion of stability. So what are we saying? So initially the particle was in this orbit. I am going to show it schematically. The charged particle was here. If there were no radiation, it would have continued to move at this radius, but because of radiation it loses energy, it keeps falling, so it essentially keeps on spiraling and collapse here. In other words, if you wait for a sufficiently long time, the size of the atom should be the size of the positive charge distribution, which we know is something like 10 to the power of minus 15 meters. The big question here is, what is the time scale for the particle to continuously decelerate and fall into the nucleus? We have to answer that question. If it is of the order of the age of the universe, we will say we won't care. It is hardly emitting at all. But Maxwell's equations also tell you what the time scales are, and these time scales are all of nanoseconds, 10 to the power of minus 9 seconds. But we know that our universe has been there according to the Big Bang theory for 10 to the power of 12 or 14 seconds, and our earth has been there for a billion years, 10 to the power of 9 years, so on and so forth, and atoms have been there. That means there is something seriously wrong with this picture. So now you can see we are again at the crossroads of the contradiction of something that we observe with the classical laws. Planck saw a contradiction with the classical law with what he observed. So he gave rise to, he postulated the existence of a quantum of photon because he could not understand the black body radiation. Einstein saw a clash of consequence of classical theory, wave theory, for example in photoelectric effect. So he made use of the concept of the photon, the quantum of energy. Again you see in the atom we are finding a conflict with a consequence of Maxwell. So at every point we are finding a conflict with the concept of a classical wave and a radiation from a charged particle. So perhaps here also Planck hypothesis or a quantum notion plays an important role. And this is where Bohr comes into picture, and what he did, was to bring in some of the ideas of Einstein and Planck and try to understand the results of Rutherford. Now, it is one thing to say that the charged particle radiates, it is another thing to see good evidence for that. And fortunately for us today, we have great evidence starting from the laboratory scale to the astronomical scale. So, let me show you some pictures for example. This is a radiation from a synchrotron. So, what is a synchrotron? You produce a large magnetic field and you let in the electron, and the electron keeps going round and round in the magnetic field. But at some point it passes through a tube where it will get accelerated. So, it comes with a higher energy, then again it will go round, again it gets a kick, so on and so forth. It is called a synchrotron because you have to synchronize the period over which it accelerates with the period of the orbit. In relativity it is a little bit complicated, never mind about that. But if you believe in Maxwell, consequences of Maxwell's equation, my charge is continuously accelerating, therefore it should also continuously radiate. So, this figure shows you the energy of the emitted photons and their number, the number density against the emission. This is a figure taken from one of the synchrotron results. So, you can actually see it even in the visible region. These of course are in very, very high energy in the GeV range. Is that okay? You see that the radiation is emitted over the full spectrum. Is that okay? If radiation is emitted over the full spectrum, that means it is a very, very good evidence for the fact that accelerated charged particles radiate. This is another curve coming from a cosmological astrophysical object called active galactic nuclei. Active galactic nuclei support a very, very large magnetic field in which the charged particles start getting accelerated and they start emitting radiation. So, you see this is the intensity of the radiation against various wavelengths. So, this is the characteristic synchrotron emission, that is what is shown. Then of course, lot of other things happen, but the more important thing is that you see that it starts in the radio region and it comes to the infrared and almost borders on the visible, and of course it will continue. After that it is not the synchrotron, lot of other processes take over, but still there is acceleration. It goes on to the visible region, then it goes to the ultraviolet, that is beyond the violet, and then it goes to the X-ray region. So, these have been observed and have been perfectly correlated with the consequences of Maxwell's equation. So, this is another particular example, and here is actually a visible picture in the space where a jet is coming because of such an active galactic nucleus. So, whether it is lab in your accelerators or whether it is the cosmic accelerators in outer space, Maxwell's equations are very well established. So, we have to ask ourselves, what is happening in the case of an atom? Why is it that my atom is not decaying? Why are my electrons not collapsing into the positive charge? So, you see, however you may look at it, we are in continuous trouble. The Plum Pudding model was first of all ruled out. Even if it were there, it is difficult to explain the stability of such a system from electrostatics. Rutherford tells you that it is not Plum Pudding model, probably it is a planetary model, but then it is contradicting the classical law that accelerating charged particles must radiate. It is a very, very important question. So, when we are speaking of the discrepancy between what is observed and what is predicted, an atom should live for 10 to the power of minus 9 seconds, whereas atoms have lived for 10 to the power of 12 or 10 to the power of 14. So, there is a discrepancy of the order of 10 to the power of 20. That means there is something extraordinarily radical that is happening, and that is where again the quantum hypothesis comes to be very, very important. So, this is something that we have to remember. Now, does it mean that the atom does not radiate at all? We did not say that. We only said that the atom is stable. That is what we said. Now, however, I can always excite an atom. How do I excite an atom? For example, if I heat a material well enough, my electrons will escape. In photoelectric effect, what happens? Radiation comes and hits the atom and the electrons will escape. So, if you go back to the classical picture, let us go back to the classical picture. You can imagine that there is this nucleus here and there is an electron, let us say. Now, what is going to happen is that the electron may be in this particular orbit. I can supply energy and the electron can go to this orbit. That is what can happen. Now what will happen is that, of course, classically speaking, all orbits are allowed in between these two orbits. So depending on how much energy I supply, it will go and sit in the orbit. Now there is nothing that tells me that the electron in the excited state in the higher orbit should not come to the ground state. So this is the minimum energy, let us say. So when I speak of the stability of an atom, what I mean is that there is a minimum energy state of the atom, and after that my electron will not further fall down. But if it is an excited state, so it can go here, it can go here, this is one orbit, this is another orbit, these fellows can always come. So how do they come? When they come here, classical theory will tell you that they should continuously emit radiation. So let me go back to the previous picture. In the previous picture, you see the radiation is continuously emitted. Or look at this picture, the radiation is completely continuously emitted. So there are two aspects. One is the stability, and another is the nature of the radiation that is emitted when the atom is excited. It is sent to a higher orbit. That is what we are looking at. And spectroscopists who have been studying atoms not only on the earth, for that matter even on the sun, very carefully, they find the emitted radiation is not continuous, but it comes in discrete lines. Only some of the wavelengths are allowed. So in your course you will learn many names: Lyman series, Bohr series, bracket series, and then you have Fund series, and then you have some other series. It goes on and on and on. And here is an example of what is called as a Lyman series. So you see, it starts with a wavelength. So actually we should start with the largest wavelength, about 1200. This must be angstroms, 1200 angstroms, and goes all the way up to 900 angstroms. That is what we see in the case of Lyman series. There are further classifications: 972, 1026, 1216, etc., etc. Never mind about that. So in this region we have what is called as the Lyman series. We will come to that in a minute. Okay. Now there is another series called the Bohr series. Is that okay? Lyman series is not in the visible region at all. Okay. But Bohr series is in the visible region, because you see red, you see blue, you see violet. Is that okay? Here the wavelength is decreasing as I go in the other direction. 4017 probably is almost already away from this one. Then you go to other regions. These are all blue region. After violet you get ultraviolet essentially. So if I go back and look at the Lyman series again, the wavelengths are very small. So it is all in the ultraviolet or the X-ray region, whereas here the wavelengths are larger, and that is what you see. And there you see there is a very peculiar spacing between them. What is the spacing that you see? Between these two there is a very large spacing. It is smaller, it is even smaller, it is even smaller. So the spacing becomes smaller and smaller as you move along the direction of what? Increasing wavelength. Now let me see, decreasing wavelength or increasing wavelength, decreasing wavelength, and you see the same thing here also. Okay. So you are starting with a wavelength of 1250. As you keep on decreasing it, that is what we are doing in the direction. In this direction, the spacing becomes smaller and smaller. This is a unified picture of all kinds of series. Is that okay? So you see there are very nice groupings, and there is very little overlap. That is the most important thing. All these are for hydrogen atom, by the way. So here is your Lyman series. So you see ultraviolet extends up to this point. Bohr series starts in the visible region and extends up to this point. Then you have what is called the Ritz-Passon series, which partly overlaps with the visible region. It is almost at the border of the visible region, and then goes, and then you have the so-called bracket and the Fund, so on and so forth. There is one more. And the fact is that they have no overlap and also similar structure. As you move along this particular direction, the space becomes smaller and smaller and smaller. We have to understand why is the spectral distribution discrete and why are they grouped in this particular manner. That is the question that we have to answer. Now there is a gentleman called Rydberg who studied this in a very careful way, and he came up with a beautiful formula, and that was the following. He found that the wavelength emitted depends on a universal constant into 1 over n1 squared minus 1 over n2 squared. That is what he found out, where n1, n2 are integers. So probably I should write it as n2 squared minus n1 squared. That is what he found out. Now the interesting thing is, if you put n1 equal to 1 and n2 equal to 2, 3, etc., etc., this is what is called Lyman. If I put n2 equal to 1 and take n1 equal to 1 and n2 equal to 3, 4, etc., etc., this becomes Balmer. In fact, as you keep on shifting the value of n1 by 1 unit, then you will hit Ritz-Passon, bracket, and so on and so forth. Ry is a number to which we have no clue, and what is this called? This is called the Rydberg constant. Rydberg constant, and of course, if my atom is sitting in the state corresponding to n1, the orbit corresponding to n1, I don't know what it means. If my atom is sitting there, there is no further decay, there is no further emission. That is what we find, and this we have to understand. So let us collect all the results that we have learned so far from Rutherford scattering. The first one is that atom is mostly empty. So what are we saying? We are saying that there is a positive charge Ze concentrated at the center, and our electrons are moving in orbits, and the size of this is of the order of 10 to the power of minus 15 meters, whereas this distance is the order of 10 to the power of minus 10 meters. That is the statement that we are making. But then it also throws up a problem, and that is, this model is not in agreement with observations, other observations. What are the other observations? Number A, spectral lines, spectra of radiation are discrete, as we saw, but classical theory predicts it should be continuous. So it is not continuous. It is not continuous. Even more importantly and spectacularly, the atoms that we are looking at are all stable. Whereas classical electromagnetic theory would predict that over a period of about 10 to the power of minus 9 seconds, electrons should have collapsed. Electrons should have collapsed into the nucleus. Electrons do not collapse. So what does it mean? This means there must be a lowest orbit which is stable. Experiments predict the existence of a lowest orbit, the lowest orbit, which must be stable, but this is not allowed by classical electromagnetic theory, because classical electromagnetic theory tells me that every time there is acceleration, there must be radiation, and there is no known law that protects an atom. So we have two tasks at hand. Two tasks. Understand discrete spectrum to understand stability. And the solution to both these problems was given in one shot by Bohr. So, in giving this solution, he made assumptions which were apparently self-contradictory or certainly in contradiction with known laws of physics. So, for this reason we do not call it as a theory, but we call it as a model, and today all these phenomena or all these developments are dubbed as old quantum theory. The real quantum theory started only after Schrödinger wrote his equation and Heisenberg gave his uncertainty principle. That is something that we have to remember. So, what we shall now do in the next 10 minutes or so that I have is to give an introduction to the Bohr model. I will explain what the model is, and in the next lecture I will work out detailed consequences of this model. So, what are the assumptions that Bohr made? So, let us start with the Bohr model. Bohr was highly impressed by the work of Planck and Einstein, and Planck and Einstein essentially had introduced a new fundamental constant h bar or h. H bar is h by 2 pi, we saw that in the next class, and let us remember this has a dimension of energy into time. But more importantly for us, h has the dimension of angular momentum. This is very important for us. Every time we think of h, so far we have been thinking of either energy or momentum. E equal to h nu, P equal to h by lambda. But now, if you look at the dimensional analysis, this has the dimension of not only energy into time, but also angular momentum, and this is something that Bohr exploited. So, one thing is to exploit a new physics that might perhaps come from the invocation of Planck's constant, and the second thing that Bohr did was to actually enunciate a rule. So, when I say that I enunciate a rule, it is like passing an order. That means it is an ad hoc assumption, and the rule emitted was that emission of radiation by accelerating particles, electrons in our case, are also governed by new physics. That is to say, mere Maxwell's equations and a classical orbit are not enough to understand the nature of the atom. So, that means we need new principles. That is what Bohr did. But Bohr still kept features of classical mechanics, just as Einstein kept features of classical mechanics and Planck kept features of quantum mechanics. Therefore, Bohr model is what we call today to be semi-classical. So, just as in the experiments of photoelectric effect or de Broglie waves, we find that the same object can be sometimes represented by a wave or a particle, the same entity. In a similar manner, when we discuss a model like the Bohr model, for a moment we make use of the classical law, at another moment we make use of a quantum law. We do not try to reconcile the two, or we do not try to understand how or where one law should play a role and another should not play a role. That is a very important thing. We do not do that. We simply enunciate the rules. We compare with the experiments, and if it agrees, then we can try to build a more general theory. That is the most important thing. So Bohr model is a semi-classical theory. So what is it that Bohr did? And I should remind you that what de Broglie did was actually inspired by what Bohr did. That is something that we have to remember. So this is some kind of a brief introduction. So in the next lecture, I will give you all the Bohr postulates, and then we will discuss the model tomorrow. Okay, bye.